remember correctly, only one of those is a proof. The rest are all computational. All right. So, any questions before we get started? Remember, we don't have class this Friday. That Friday, the 20th, you'll have your exam as well. So again, you'll be able to start it at 8 o'clock, just like before. And we'll talk a little bit more about that next, after we get back from break. Any questions about anything at all? No? Well, good. I'm glad the video made sense. And I really did want to just make it more of a computational idea because we'll talk a little bit more of the concepts in class. But so one of the things I mentioned on the video was I asked you to go back and look at the way we set up the matrices. Did you notice anything about the way the matrices are set up and the vectors themselves to start with? How the matrices were set up in terms of the vectors? Did you look down the columns of the matrix and then look at your vectors that you started with?
Oh,
yeah, they go straight down, right? Yeah, so when I went on the video, I went up and set it up as a system of linear equations and then wrote the linear system of linear equations in the augmented matrix form. But if you notice, those coefficients that came out for looking for the constants were just the coefficients on your particular vectors down the columns. So it could have just immediately just stuck it in matrix form and done it that way, and not had to go through and set up a system of linear equations to start with. We'll look at a little bit more of that today as we get into more of the concepts. But the problems that we'll be doing as far as that goes will be relatively straightforward. And also, I would expect that you'll do the row reductions on your calculator, so you don't have to do them by hand. But before we get into the linear independent stuff, let's talk a little bit more about, span, the idea of spanning sets, and also looking at how you can check span, again, by looking at the reduced row echelon form of a matrix. So in particular, let's look at number 14 on page 239 to start with. Number 14 has vectors in R4. So it has V1 is 2, 1, 0, 3. V2 is 3, negative 1, 5, 2. And V3 is in negative 1, 0, 2, 1. So the problem asks, which of the following are in the span of these vectors? So the vectors that they have are, just to write them down, the first one they have is 2, 3, negative 7, 3. The second one is 0, 0, 0, 0. Third one is 1, 1, 1, 1. And the fourth one is, can't see it because it's off the bottom of the screen, negative 4, 6, negative 13, 4. So just to remind again what we mean by span, the span of a set of vectors is the set of all linear combinations that you can make from those vectors. So pick any constants that you want. Take any constant times V1, any constant times V2, any constant times V3, add it together. That's in the span of those vectors. So it's all the set of all linear combinations of the vectors. So what this problem is actually asking us for that first vector is, for this one, is asking, do there exist constants C1, C2, and C3 so that C1 V1 plus C2 V2 plus C3 V3 is equal to that vector. That's what the problem's asking, right? Because the left-hand side of this equation here is an arbitrary linear combination of the V1 out to V3. We want to know, is it possible to find the three constants that give you that vector? Now, it might be the case there's multiple sets of constants that work. We're just interested in knowing, is there at least one? Now, from the video, when we're talking about linear independence, that's when we're looking to see if there's only one way to do it, if we can do it, right? There's only one way to do it. Talk about that uniqueness idea. But for span, we're just interested in, can we do it? There might be more than one way to do it, but can we do it? Okay? All right, so, but the concept is the same. Notice in the video, when you were trying to figure out a set of vectors was linearly independent, you set up a system of equations and row reduced, right? That's the same thing that's going to happen here, right? I need to figure out, in order to get this vector out, I have to get 2 out from the first components of the 3 vectors. I have to get 3 out from the second components, and so on down the line, right? So we have to solve we need to solve the following set of equations. Well, when I take C1 times V1, I get a 2C1 in that first component. When I take C2 times V2, I get a 3C2 in that first component. When I take C3 times V3, we get a minus C3 in that first component. What is that going to have to equal? 2. Yeah, because the first components have to be the same, right? So tell me what the second equation is going to look like.
C1 minus C2 equals 0.
Okay, and 0, yep. Equals 3. Good, because it has to equal that second component, right? What about the next equation?
Plus 2C3 equals
-7, okay. And the last one?
3C1 plus 2C2 plus C3 equals 3.
Good, cool. Everybody see where that system of equations is coming from? We're just equating components on left and right side. Just like it was on the video, it's just on the video since we were doing linearly independent, we had 0 on the right hand side every time. It's the same concept though. All right, notice in this one, we have more equations than unknowns, don't we? Right? So when we get more equations than unknowns, we get what are referred to as overdetermined systems. We don't need all of this information to get a unique solution if there is one, right? And with overdetermined systems, we get issues with, perhaps, when we try to solve, of having too much information, right? So for example, if I think about a simpler example, if I have 2 lines, then I know if they intersect, that gives me the solution to that system of 2 equations with 2 unknowns, right? But as soon as I introduce a third equation, if it's going to have a solution, where does it have that third line have to go through? The same point, right? If it's going to have a solution, it's going to have to go through that same point. That means it has to be, it's pretty much useless information for as far as determining the system, right? And really, it can just cause a problem, because if it doesn't go through that point, then what are we going to say about the system? Is there a single value that satisfies all 3 equations at the same time, or a single point that satisfies all 3 equations at the same time? No. Okay. So when we have these overdetermined systems, is when we get issues with being able to solve these equations. A lot of times, right? We don't necessarily have to, but it's possible. So this is why might be a little bit more interesting question. And in fact, you could probably imagine scenarios by changing one of these numbers that you'll definitely be able to get this not having a solution. So that's one of the points of this problem. But let's see if we can solve this. If we set up the augmented matrix, we would have 2, 3, -1, and 2, 1, -1, 0, 3, 0, 5, 2, -7, 3, 2, 1, 3, right? Notice again, this is what I was mentioning right at the beginning of class. Do you see any relationship in the columns of this matrix and the vectors that we started with? Yeah, they're the same, right? We just end up writing them down, the columns of the matrix. And in almost everything that we do, there's going to be one exception, which is kind of weird, but in almost everything that we do, this is exactly what we're going to do if we're going to use row reduction to help us answer a question. You're going to take the vectors that you're interested in and put them in columns of the matrix and row reduce. This is typically what's going to be the first step in everything. Because again, how did we start this problem off? We set up a system of linear equations. How do we typically solve a system of linear equations? We row reduce, right? So in a lot of problems that involve actual computations with vectors, one of the first steps that you're going to do is put the vectors as columns in a matrix and row reduce. Okay. All right. So to do that, someone's going to have to read the numbers to me because I'm not going to remember them. All right. So let's go to second matrix, and let's just edit matrix A. I need a 4 by 4. And let's see, the first row is 2, 3, -1, and 2. The second row is 1, -1, 0, and 3. The third row is 0, 5, 2, and -7. And the fourth row is 3, 2, 1, oops, not on, 1, and 3. Can I get those entered in okay? Cool. I was tapping on the screen, so makes it a little more difficult for me. All right, so anyway, that's our matrix. So let's quit out of here and then go back in. Don't hit the sign button. Go back in here and grab math, reduced row echelon form is that one up there. B, too far. B, and then I want to do A is what I want to row reduce. There we go. All right, so remember again, we're trying to figure out if this is in the span. It's in the span if I can find the constants. So what we have to do is we have to interpret this information from the matrix we're given. Okay? So, do we have a solution to this system? Yeah, we do, don't we? And the reason why is we've got this last column, or excuse me, this last row here is a row of zeros. We don't get any inconsistency, right? So we really do get a solution here. We get C1 equals 2, C2 equals -1, C3 equals, C3 equals -1 as well. You can check your answer, correct? You just go through and plug in the numbers and see that those vectors really do, those constants really do give you the linear combination that you need. By the way, we could have also checked at the same time whether or not this set was linearly independent. Remember, as I was talking about in the video, to show linear independence, you would have zeros on the right-hand side here, correct? Now, if I'm row reducing with a bunch of zeros in that last column, what's the last column always going to be? Zeros, right? There's not going to be anything here, correct? So that doesn't really do anything for the row reduction, does it? And then we have to make sure that we get unique solution, correct? We have to get C1 equals 0, C2 equals 0, C3 equals 0. Would we have that in this case? Yeah, so this set would also be linearly independent. That set of 3 vectors would be linearly independent in this case. Just trying to tie it to the stuff that you looked at the video. We're going to talk more about linear independence here in a bit. All right, so anyway, since we can solve this, we say that the vector was in the span. Questions on any of that at all? Well, we'll do the other ones here in a second.
Was that your final answer? Like that is in the
It just asked it as whether it was in the span, and so this one is yes, it was. Now, if it asked you to find the constants that give you a linear combination, then you would use the 2, -1, -1 as the solution. Yeah, but this one, the answer is just yes. Okay. All right.
So we need to go through and check and see if all of them are, or is there only going to be one?
No, we need to check all of them. This is asking which ones are. But I was going to show you how we could do it all at once. So we only have to do one row reduction. Okay. So let's go back over and edit this matrix. So what I'm going to ask is when we set up the system of equations, this 2, 3, and -1 were the first components of each of the vectors, right? The 1, -1, 0 were the second components, and so on down the line. If I put a different vector over here and ask if it's in the span or not, is this left-hand side going to change? I don't know. When I row reduce, or when you row reduce, or when we row reduce, use whichever pronoun noun you want, do you mix columns? Do you go across columns and do operations? No, everything's done down, right? So if I put another set of numbers here and do the row reduction, is that going to change how I would row reduce this part of the matrix? No. So I might as well have just put them all in the columns at once and did the row reduction one time. So let's go in here and edit this matrix. I need 3 more vectors on the end because the problem had 3 more vectors in it, right? We agree? So I'm going to change this to 7 columns rather than 4. So I want 0, 0, 0, 0 down that next column, which is not interesting. 1 and -4 here. Then let's scroll across. I want 1. I did just hit the down arrow. Thank you. All right. So one's down that column. And I want the -4, 6. Oops, and of course I hit the enter instead of the down. And -13 and 4. So all we're doing here is solving 4 different systems of linear equations at the same time by using the fact that our coefficient matrix isn't changing, right? And when we're row reducing to solve the system of linear equations, we're only interested in actually row reducing the coefficient matrix, right? That's the only one that's of any interest to us. So the same set of row operations that we do to solve for the first column of constants is the same set of row operations we'll do for the second and the third and so on down the line, right? So we only need to do the row reduction one time. So let's quit out of here. And since I already have the reduced row echelon form of A as with the last entry, I can just pull it up. There we go. So remember again, the first 3 columns here are correspond to the coefficient matrix, right? The last 4 would correspond to the vectors that we had plugged in. There's one of those that we can't solve for. Which one is it?
1, 1, 1, 1.
Yeah, the 1, 1, 1, 1, right? Because that gives us an inconsistency, doesn't it? I would have 0 equals 1 here. Everybody see it? Okay. So the third one, the 1, 1, 1, 1 vector is not in the span because I can't solve that system. It's inconsistent. The other ones are in there. And in fact, I can read the coefficients off, right? just like we did before. So to get the last vector, whatever that one was, you take 3 times the first minus 3 times the second plus the third. We'll give you the last one. That's what that says.
I have a calculator question.
Mhm.
How do you scroll like sideways?
You should just be able to maybe highlight it again. That's weird.
I don't know.
You should be able to.
It just doesn't do it.
That's weird. Just make sure you don't touch anything else before, when you want to scroll before you scroll.
Okay. I've never been able to get it to scroll, so.
That's weird. Smack it around. That'll help.
Sounds good.
Yeah, throw it against the wall. Good. Drop it in some water. Be great. All right, this okay? This idea? All right. So, what's interesting about span is, well, this should be interesting about span, is notice that when we row reduce the coefficient matrix, the way we're going to check to see whether or not it spans is whether or not we can always solve the system after we row reduce. Well, notice that here, no matter what we do with the coefficient matrix, when you row reduce, you're always going to get a row of zeros at the bottom, right? You don't have enough rows to get a pivot in this row, correct? So no matter what here, you don't have enough vectors to span all of R4, because I won't always be able to solve this, right? When we row reduce, you have 1, 1, 1. I can't get a 1 down here. So again, you can imagine scenarios like we have right here that you're going to end up with inconsistencies. So there's going to be vectors in R4 that you won't be able to represent using this particular set of vectors, I mean. Remember we had those problems back in chapter 1 that said, find conditions on the B1, the B2, the B3 so that you can solve the system? Remember those? Right? And we had to keep track of what was going on with the B's because a lot of times you get a row of zeros on the left-hand side. And so then that whatever you did with the B's had to be 0 as well. Remember those problems? Okay? The reason why you were doing those problems is going to this stuff. When we row reduce this matrix, we're always going to get a row of zeros at the bottom. No matter what we try to do, there's too many rows, right? So like there will be scenarios you can think of B1, B2, B3, B4. Since there's always going to be a row of zeros here, if you start playing with the B's, you know those B's will have to satisfy a certain equation that equals 0, right? A certain expression that equals 0, I should say, right? And those were the conditions that we had on the B's that would have to work. So when you're doing span, you have to have, especially for a vector space like R4, you have to have enough vectors in order to take up each component. Right? You need to be able to see a pivot in every single row in order to make sure that you can possibly solve in any situation. It's not a guarantee, but I can guarantee you won't be able to if I can't get a pivot in the last row. Right? So to be able to span R4, bless you, to be able to span R4 here, we have to have at least 4 vectors. Because I need to be able to get a pivot in all 4 rows. Does that make sense?
Yes.
Okay. Now, it's possible I may need more. We'll talk more about that later. But in order to be able to span R4, you have to have at least 4 vectors, no matter what. And that makes kind of sense, right? Because you have 4 components that you have to account for. Right? Kind of makes sense that would be the case. So let's see if we can do another one like this. So, let's see, this is number 9. I'm going to change the directions a little bit. Same page, but number 9. We've got P1 is equal to 2 plus x plus 4x squared. P2 is equal to 1 minus x plus 3x squared. And P3 is equal to 3 plus 2x plus 5x squared. And I'm going to ask instead, is the span of P1, P2, P3, that's a P, not a B, P3 equal to all of P2? Remember that the P sub n is our notation to denote polynomials of degree less than or equal to n along with the zero vector. So before we answer this question, let's see if we can think about this in terms of the way that I just mentioned with R4. We said that in order to be able to span R4, to make sure that any vector in R4 can be written as a linear combination of a set of vectors, I need at least 4 vectors. Because I need 4, basically I have to fill 4 spots, right? So think about your vectors in P2, or second degree polynomials. How many spots do you need to account for in second degree polynomials? Think about it in terms of the components of the vectors. How many spots do you have to account for in second degree polynomials?
3.
What are the 3?
Yeah, term for the constant, the x and x squared.
Good. I need the constant, the x coefficient, the x squared coefficient, right? I've got 3 things that I have to account for. So I probably am going to need at least 3 vectors, 3 polynomials to span it, right? Because I have 3 pieces of information I need, right? I have to know what the constant term is, I have to know what the x term is, and I have to know what the x squared term is, right? Okay. And here we do have 3 pieces of information, so at least I think I have a fighting chance, right? It's not a guarantee by any stretch, because it's possible that one of these is in terms of the other 2 and basically becomes unnecessary, right? That's the whole idea of that linear independent idea, which we're going to get to, okay? But at least I have a fighting shot in order to be able to span P2, right? I've got 3 vectors, so I hopefully have enough information to give me whether or not this is going to span. All right, so think about it again. If I've got some arbitrary a plus bx plus cx squared that I'm trying to find, right? Just some arbitrary polynomial in P2, we want C1 P1 plus C2 P2 plus C3 P3 is equal to this polynomial. That's what we need, right? That's what it means to be in the span. A linear combination of the p's gives me this polynomial. That's what it means to be in the span, right? Okay. Well, again, we set this up by equating, in the last problem, we equated components of the vectors. In this one, we'll equate like terms, right? Equate constant terms, equate x squared terms to get our system of linear equations. So, like Alex said, we have to match constant terms, x squared terms. So what equation do you get from trying to match your constant terms? What equation would you get?
C1a plus C2 plus C3.
Well, the a is on the right-hand side. We're trying to use these vectors here.
Oh, sorry, just 2, 1, 3.
So the 2c1 plus c2 plus 3c3 has to be a, right? That's what getting the matching of the constants, right? What do you get for trying to match the x terms?
X, C1.
So not x, just this is all we need is the coefficients, just c1. Good. 1c1 minus c2 plus 2c3 has to equal the b. And then what's the one for the x squared term?
4c1 plus 3c2 plus 5 equals 2.
Good. So again, all we're doing is running the constants through, right? C1 times the first one, C2 times the second one, C3 times the third one, and equating like terms, right? Constants have to match, x terms have to match, x squared terms have to match. Now again, what we're trying to figure out here, notice I didn't give you a specific A, B, or C. I'm asking you, no matter what you plug in for A, B, and C, can you solve? That's what the problem's asking. If I take an arbitrary polynomial in P2, can I write it in terms of the P1, P2, P3? That's what the problem's asking, right? Okay. So when we set up the system, or set up the matrix again, when we're interested in row reducing, I want to know, can I always solve this? So am I really interested in what's on the right-hand side of the equality? Or do I just want to know that I can always solve this? Do I get a pivot in every row? Do I care what's over here? No. So I'm not even going to bother putting this in my matrix when I row reduce. I don't care. What I'm saying is, I don't care what the answer is. I just want to know, can I find an answer? I'm not worried about an explicit answer. I just want to know if I were to plug in values for A, B, and C, I can find the answer. Okay? So what that means is that if we row reduce this and I get a pivot in every row, it doesn't matter what the A, B, and C are. I can always solve it. Right? But if I row reduce and don't get a pivot in one or more rows, I can't always solve it, because you can imagine scenarios where you would row reduce and then down here you'll get something that's not a 0. Right? Because think about what you do. You would row reduce this, you would have 0, 0, 0, and then you would have some expression over here with A, B's, and C's that has to equal 0 in order for it to be consistent. So just pick an A, B, and C that wouldn't make it 0, and it's inconsistent. Right? So all we're interested in is this matrix on the left. Now again, do you notice any relationship between this matrix that we came up with and the original vectors? Looking at the columns, do you notice anything?
Constants just go down the column.
Yeah, it's just the coefficients, don't they? The 2, 1, 4 is the coefficients on the first one. The 1, negative 1, 3 are the coefficients on the second one, and so on down the line. Just like we did with the vectors in the original problem, right? That's why I said, when you're checking these things, a lot of times you're just immediately going to put things in columns of a matrix and row reduce. It's the same type of problem. Okay. All right, so let's do that. Or did somebody already do it?
Yeah.
Okay, cool. Then I don't have to do it. All right, so if we put this in your matrix or in your calculator and you put it in reduced row echelon form, what do you get? Good, cool, good. That's what we should get. So, what's your answer? Can you always solve this system no matter what A, B, and C is?
R. Yes.
Yes, we can. So does the span of those three vectors end up being all of P2?
Yes.
Yes. Good. So our answer to our original question then is the span of these three vectors is all of P2. Now again, the whole point of this is I want to show that my vectors in my vector space, in this case my polynomials in P2, all can be written in terms of three specific polynomials. And we're going to use that information later on to say, okay, well, if I know what happens to these three polynomials, I know what happens to everything. That's the idea behind this. And I know some of the examples I've given to you come from differential equations. Well, I think I mentioned this the other day. If you look at this differential equation, you can show that these are both solutions. It's not hard to do. Just take the second derivative and the first derivative and plug it in, right? Okay. So there's a whole bunch of functions that satisfy this differential equation. I found 2 of them, but now I know that every single one of them, there's some other theory about that goes behind it, but since this is a second order equation, and I found 2, I now know what they all look like in terms of these 2. Right? All of them have to look like a constant times the first plus a constant times the second. I now know what they all look like. That's a powerful statement, right? I only had to find 2, and now I know all of them. Okay? I know what everything in the set of all solutions look like here. That's the same thing we're saying here. I know that every single polynomial can be written in terms of these 3. So if for some reason I needed to solve a problem that involved finding just these 3 polynomials, then I would know what they all look like for any polynomial. Okay? So we're trying to break down the set of infinitely many things into a finite set of things to analyze instead. You do this a lot in other scenarios. Okay? But that's what this whole point of this is trying to break down specifically what do my things have to look like. And you actually do this inherently without even thinking about it. You do this with polynomials all the time because you know that a polynomial has to have a constant term, an x term, an x squared term, and so on down the line, right? So you already know things like the span of 1x, x squared up to xn is your Pn. You already know this. You do this all the time, right? Because to get an nth degree polynomial, you have to have a constant term, an x term, an x squared term, and so on, right? This is just allowing us to be more general. Instead of saying, okay, I have to use 1x, x squared, and so on, I can use other polynomials and get to the same place. Well, now, whether or not that's useful is up for debate. We'll talk more about that later, okay? But what this is saying is, okay, I'm just doing this generally now. I don't have to worry about it being specifically something times the 1 plus something times the x plus something times the x squared and so on, right? I'm saying that now we could say, okay, it's something times the p1, something times the p2, something times the p3 with different polynomials. Okay. It's just making it more general. Yeah, Megan.
So when we get solutions, will they always be positive?
Well, maybe they're positive. The coefficients, they don't necessarily have to be positive. They can be negative.
Okay.
The constants, the C1, C2, those could be negative. Those can be, those have to be scalars.
Okay.
All right, questions on that before I switch gears over to linear independence? Because I'm going to do it right now. We just row reduced that. Is that set of vectors linearly independent? So let's think about what the definition was. The definition of linear independence says if you have a linear combination that gives you the 0 vector, then you had to use the constants that were 0, right? That was on the video, correct? It said if you have a linear combination that gives you the 0 vector, then the constants you had to use were all zeros. You didn't have a choice. Okay? So here's our row reduction. If we set up this system with zeros here, we would still have zeros here, correct? Right? So what's the solution then if I just had zeros here?
0.
Yeah, 0, 0, 0, correct? So would you say this set's linearly independent? Yes, yeah, exactly. So notice it's the same problem, isn't it? Again, put your vectors in columns, row reduce, see about the answers. Now, for linear independence, of course, you always end up with a homogeneous system of linear equations that you're trying to solve, right? Because you're trying to say, is there a linear combination of the vectors that gives me specifically the 0 vector, right? You're not doing it for an arbitrary vector. Arbitrary vector is span, right? We're trying to see a very, very specific vector. Is there a non-trivial linear combination that gives me the 0 vector? How do you get non-trivial solutions to homogeneous systems? What has to happen to get non-trivial solutions to homogeneous systems? What do you have to see? You have to see a free variable, correct? Which means you have to have a column without a pivot, right? To get a free variable, right? Okay, so let's compare the two that we've talked about now. This, we were talking about span. We know it doesn't span if a row doesn't have a pivot, right? It's not linearly independent if a column doesn't have a pivot. Right? They kind of go hand in hand here, right? So, if it's going to span your entire vector space, you have to have a pivot in every row. If it's going to be linearly independent in your vector space, there has to be a pivot in every column. So let's think about it in terms of the size of the matrix. If it's going to span and be linearly independent, what kind of a matrix are you going to have? What's the dimensions going to have to be?
Square.
It's going to be square, right? Right? If you have more rows than columns, you can't get a pivot in every row. If you have more columns than rows, you can't get a pivot in every column. Right? So in order for it to be linearly independent and span your entire vector space, you're going to have a square matrix to start with. If it's not square, it can't do both. Okay? So notice again, it's the same idea to start with. You put your vectors in columns, row reduce, so you can answer both questions. So let's see if we can do an example here with linear independence before we knock off for the day. We'll talk more about linear independence after break as well. All right, so let's look at, this is number 3 on page 248. So we have the vectors, this is part A, but the vectors 3, 8, 7, -3, 1, 5, 3, -1, 2, -1, 2, 6, and 1, 4, 0, 3. Given the size of these vectors, the way I've written them, what spaces are these coming from? R4, good. All right, so let's just ask both questions. Treating it as a set, are these vectors linearly independent? Do they span all of R4? Well, first question, do we even have enough vectors to span all of R4? If I'm asking a span question, I need to know. Again, how much information do we need to know about R4? How many components does a vector from R4 have? 4. So if I'm going to have enough information, how many vectors am I going to need? 4? Do I have 4 vectors? Yeah, okay, so at least I have a chance of it spanning, right? Okay. Also, if I make my matrix of these as the columns, is it going to be a square matrix? Yeah, there are 4 components and 4 vectors, right? So think about when you row reduce it. To span, we have to have a pivot in every row. For linear independent, we have to have a pivot in every column. To have both, to have one means have the other, right? If you're going to have a pivot in every row, you're also going to have a pivot in every column if it's square, correct? So these two answers are going to be either both yes or both no. Right? There's not going to be one or the other because it's not. The only way you can have one and not the other if it's not square. Okay? If it's square, it has to be both or neither. Right? Because one requires a pivot in every row, the other requires a pivot in every column. If it's square, you have the pivots are going to line up down the diagonal. If it's going to be both, right? All right, so first thing we do is we take these suckers and put them in a matrix as columns. Anybody type this in? Okay. And when you row reduce, what'd you get?
I did agree.
Good. So what do you say to both of these questions?
Yes.
Yes, good. So again, referring back to what I talked about on the video, why do we care about linear independence? All right, so for span, the reason why we care about span is because we want to make sure that everything in the vector space is expressible as the smaller set of vectors. The whole point of this is, if I'm trying to analyze a property of your entire vector space, the goal hopefully is to analyze the properties of the smaller set, and then use the fact that I can write every single vector in the space in terms of this smaller set of vectors, and get the property about the whole space. That's a lot simpler question, right? These vector spaces have infinitely many vectors in them. Unless you only have one vector, there has to be infinitely many. Okay? It's possible you could have a vector space with exactly one element in it. If it has more than one, then it has to have infinitely many. Without a question. The reason for that is because the closure of scalar multiplication has to work for every single scalar. Okay. I should say this because we're using real numbers here. If you have what are referred to as finite fields, then what I said is false. But we're not doing those. that's more advanced than what we're doing in this class. Anyway, so you have infinitely many vectors. Trying to figure out properties for infinitely many things, hard, right? But if you can cut it down to a finite number of things, and then say, okay, now that I know what these properties are for this finite number of things, it has to work for everything in a vector space, that's an easier question to answer. To give you a concrete example, solving that differential equation that I wrote on the board. There are infinitely many solutions to that differential equation. Hard. Right? So instead, you find 2 and say, oh, now since I know I have found 2 of them that have a particular form, I know what they all have to look like. Easier. Right? I didn't have to try to write them all down. I wrote down 2. And said that they all have to look like it in terms of those 2. That's the idea for span. Okay? For linear independence, what I would like to know is that, okay, I have a way to write it down. For linear independence, I want there to only be one way to write it down. One representation of that vector, not multiple. Because again, that clouds things, right? I don't want to say I can write this thing in 7 different ways. I want to write it in one way. That's what linear independence allows us to do. And so then in that case, you can talk about coordinates. When you talk about these vectors in terms of their components, think about them in like 2 dimensions or 3 dimensions. What you're really working with are coordinates, right? There's a certain vector that's a unit in the x direction. There's a certain vector that is a unit in the y direction. What you're saying is, I can write every single point uniquely in terms of an x unit and a y unit if I'm talking about points in the plane. Right? And write down not a set of coordinates, the set of coordinates. Right? That's why we care about linear independence, is because of that uniqueness piece. Okay? So again, span is to try to cut down an infinite problem to a finite one. Independence is, I only want one way to do it. Okay? That make sense? We're going to talk more about this after break. I will post a video, probably Sunday, so basically making sure that you think about linear algebra again at least at some point before you come back into class on Monday, because it'll be a while. All right? So we'll do more of this. We're getting to the idea of what's referred to as a basis of vector space. That'll be the last thing that we actually talk about before the test. It's new. Okay, so this is section 5.3 for linear independence. We'll talk about basis in section 5.4. So 5.4 will be the last new section we'll cover before the test. All right, have a good break. We'll see you on Monday if you're traveling, or the Monday after. If you're traveling, travel safely.
already.
What is that?